Hello, everyone. Welcome to our session. We are delivering a speech which is, can have cost-optimized workloads across schedule to across the region and across the cloud by leveraging some open source technology like Karpenter and Karpenter. So before we dive in, let me introduce ourselves a little bit. I'm JK from Karpenter AI, and previously I worked for AWS, and also I'm a maintainer of GCP Karpenter provider. So next is...
Yeah, I'm Michael McCune. I'm a software engineer at Red Hat. I'm also a chair and tech lead for SIG Cloud Provider. I'm a maintainer of the Karpenter Cluster API project, Kubernetes Cluster Autoscaler, and a bunch of other shenanigans.
I'm Praseeda Sathaye, and I'm Principal Product Manager at Amazon. I lead the product strategy for Amazon Internet Ingress. In past, I have worked with AWS strategic customers, helping them with modernization and cloud-native journey using Kubernetes, AWS compute services, and open source technology. I'm very excited to be here with you all. So let's get started with the agenda. Okay, as you see in this slide, we are going to first cover the challenges, what we have around the GPU resource provisioning, mostly around the capacity shortages, high cost, and regional limits. Next, we will showcase you the solution using Karpenter and Karmada for using the global GPU resource allocation. And next will be our recorded demo to show how the GPU get rebalanced between the cloud providers. And at the last, we are going to show what's next. So we will actually evolve this solution into a simpler out-of-the-box, Kubernetes-based, and we can see that how we can do the global scheduling using this solution. So let's get started with the first one, which is the challenges in GPU resource provisioning. So if you have ever tried to spin up GPU workloads in production, you must have definitely seen this error, right? It says that we are currently do not have sufficient capacity in this availability zone. So how many of our folks have seen this error message? Yay. Okay, so it is frustrating, but it is become increasingly common, right? In today's AI landscape, GPU shortage is kind of a big blocker when we are going for production level inferencing workload, right? So in some regions, there might be few hundreds of L4s available in a given region. But when you're running an inference, for example, for hundreds and thousands of inferencing workload, then this becomes a major bottleneck. And because each cloud region has their own limitation with respect to the capacity, then you cannot even rely on a single cloud provider to deliver what you need and when you need, right? So that's the first challenge we are going to solve over here, which is around availability. And now, when even the availability is there or the capacity is available, there is another challenge which comes right into our budget, which is cost, right? If you see over here, the L4, what we have, L4 GPUs, what we are seeing is the on-demand GPU pricing varies across each of the cloud providers. We are saying it could be region by region. It could be instance type by instance type. So if you, again, switch to the spot instances, they might be cheaper, but they are not reliable. So we are caught into two trade-offs, right? Whether expensive on-demand or cheaper spot instances, which could be terminated anytime, right? So either of them is not a solution if you are going for production inferencing workload. So what we really need here is a smart way to balance the cost, stability, and capacity without being locked into a single cloud provider. So the key takeaway from this slide is that no single cloud providers can guarantee you the capacity and cost efficiency at scale. So what's the solution over here? So we need to stop treating the cloud provider as silos, right? Instead, we need to think them as a GPU resource pool, which is spanning across multiple regions and multiple clouds. So imagine like you are requesting 1,000 GPUs, right? Your system need to automatically provision few in AWS, few in GCP, and few in other clouds, right? So doing this not only mitigates the GPU shortages, but also like it takes care of the cost and resiliency as well. But managing this kind of pool is very complex, I would say. You have to schedule the workload across the cloud. You need to handle the failover. You have to handle the spot interruptions, and you have to actually maintain the performance consistency, right? So how do we actually manage the clusters across the cluster? How do we balance the traffic for the users, maintaining the reliability even if any instances goes down? So that's where the Kubernetes native tools like Karpenter, Karmada, and Cluster API, which comes together and builds the foundation of what we call it as truly multi-cloud and multi-region GPU scheduling platform. With that, I will hand it over to Michael to talk about all the architecture and how it really works.
Thanks, Praseeda. So yeah, we set up the problem here, and I'm going to talk about some of the CNCF projects that you could use to achieve these topologies. But first, we're going to start off with what is a multi-cluster topology? What does that mean? There are a lot of different ways to deploy Kubernetes clusters. Every organization has a different opinion about these things, but this architecture that's kind of displayed on the right-hand side of the screen here is something that I see very frequently with Red Hat's users and customers. And this is what we call a hub-spoke style topology, where we're using Kubernetes itself to manage and create more Kubernetes. So we have perhaps a hub cluster that's Kubernetes, and then it makes several spoke clusters as well. But just deploying the clusters is only part of what we need to do here. We need to make sure that we can monitor everything that's happening in our clusters. We need to make sure that we can perform upgrades, we can remove unhealthy nodes, and all those things. So as Praseeda said, one of the great projects for this is the Cluster API project. And Cluster API is a Kubernetes sub-project that gives you the ability to control the infrastructure in your clusters using Kubernetes declarative APIs. And so you can see here these things in the middle, cluster, machine deployment, machine set, machine, and node. These are all the different abstractions that Cluster API uses to display the cluster in, or display the topology of the cluster in Kubernetes objects. I got to put my glasses on here because I'm getting old. But one of the nice things about this is regardless of which provider you're on, these objects look similar, and that gives you a consistent way to monitor your clusters. And it also gives you a great way to interact with them through GitOps, because you can use the manifests that go into Cluster API as artifacts that can be checked into a repository. And the nice thing about it too is it brings node health checking in from the Cluster API side. There's a way to perform upgrades using Cluster API, and you get a similar experience across all the different clouds you operate on. Now, yes, you can still express the differences on each cloud if you need to get specific features, but you'll have a consistent monitoring layer above them. So, if we can deploy clusters easily now, and we can use Cluster API to put them across different cloud providers, the next thing we want to think about is how do we automate the cluster behavior? How do we make the cluster add its own nodes and remove nodes when it doesn't need them? How can we get it to perform upgrades at regular basis? How can we ensure that workloads don't get disrupted and that we're having access to the latest hardware that we might need to? This is where the Karpenter project comes in. And the Karpenter core is also a sub-project of Kubernetes, and it gives users the ability to have an automation inside your cluster where Karpenter, when you are scaling workloads or when workloads are pending, Karpenter can look through the cloud inventory to find the best match resources and the best pricing matches as well. So with Karpenter running, it can start to automate those things for you. Another nice thing about Karpenter is it can also handle upgrades. Karpenter has a feature called disruption, where it can disrupt the cluster that it's running in order to do things like create upgrades within that cluster when it sees a drift between the nodes and the control plane, the workload nodes and the control plane. And then also, you can have it consolidate the cluster as well during these disruption events. So Karpenter can be running all the time. It doesn't need ops people to be directly involved in it, and it can find when the cluster is less optimally configured, and then it can reconfigure the cluster to use better price nodes, better resource nodes, and this just leads to better ops all around. So if we've got a way to create clusters easily, and we've got a way to automate those clusters' behavior, the next part of the story is how do we schedule our workloads so that they go across all these clusters that we have and across all these zones that we have. This is where the Karmata project comes in. And I'll give you a disclaimer to begin with. I know much more about Cluster API and Karpenter than I do about Karmata, but that said, Karmata is a CNCF incubation project that gives you a turnkey automation so that you can have it schedule jobs across different clusters. It provides scheduling policies that can allow you to define cluster affinities for your jobs. You can define cross-zone splitting and high availability balancing, and you can even get multi-dimensional high availability as well. I think it's worth noting that if you're familiar with the KubeFed project, Karmata is continuing many of the basic concepts that were defined in KubeFed and are now part of Karmata. So if we can create clusters easily, and we can automate those clusters' behavior, and we can distribute workloads across the clusters, what does this look like in practice? And this is how we bring it together. You might have a management cluster, which is what we see on the upper left here, and that's where the cluster API is managing the other clusters that it's running. That's also where our Karmata is running as well. So this Kubernetes cluster is kind of the head of our structure that we're building. And then we use Cluster API to create clusters on AWS and GCP. On those clusters, we install Karpenter to automate the behavior of those clusters. And then you can see all the way to the left, we're now creating nodes in different regions, and we're able to distribute this topology however we define. And now we've got a truly global scale, a multi-cloud scale to the topology that we're building. So with that, I'm going to hand it back to Praseeda and JK, and they're going to tell about how it's actually done.
Thanks, Michael. Okay, so now Michael has shown you all the architecture, what we'll be using in this demo and for this solution. But while bringing them together, we faced some challenges, and that's what I'm going to talk about. So the first challenge what we had is like how to control the traffic to align with the replica distribution. What it really means is how do you make sure your traffic is routed in the right proportionate with how many replicas have been distributed across the cloud providers or the region, right? And the second challenge we found is like, how do we provision GPUs cost effectively, keeping your workload stable, right? GPU pricing, as I said before, varies between providers and instance types. Spot instances are very cheaper and can be reclaimed anytime. So balancing the cost optimization with workload reliability is a very critical aspect. And the third challenge what we came to know about it is like how to distribute the replica when you deploy it first. So when workloads first start, the system need to smartly identify like how to distribute the replicas among the regions or the cloud providers without even knowing where the GPU capacity will be sufficient. And the fourth one was about handling the spot interruptions. So when cloud providers reclaim the spot resources, the platform should automatically detect the event, and it should be able to reschedule it in any other region or probably use the on-demand instances to minimize the downtime. And finally, how do we dynamically adjust the replica distribution, right? So GPU availability and pricing, as I said, could vary between the regions and providers. So systems should also be very smart to monitor these drifts. And according to that, it should be able to rebalance the replicas to maintain the optimal performance and cost efficiency. So these were the 5 problems like we had to solve to make it a real global multi-cloud GPU scheduling platform. And with that, like I'll go in, we'll talk about each of these challenges in detail. So I'll go to the first one over here. which is about how did we handle the traffic routing and control across multiple clusters, right? In this example, if you see, we have a deployment which has 6 replicas, right? And across 2 clusters, which are spanned across 2 cloud providers. So now the question is, when the user hits the global endpoint, which here is chat.com, for example, how does the 2/3 of traffic go to AWS and 1/3 of traffic will go to GCP, right? So how can we figure out that? So for that, we built a global load balancer controller. On the left side, if you see, it continuously monitors the replicas across both the clusters and through the Karmada's global view. And then when there is any change, for example, Karmada has rescheduled a replica, or Karpenter has probably spin up a new node. So in those cases, the controller will take those and then update the backend weights of the global load balancer so that the traffic can flow accordingly and proportionately. So let's take an example, right? If Karmada API has scheduled a pod in GCP, now it becomes 3 replicas over here. Now the controller is going to update the backend weights and actually distribute the traffic 50% across because each cloud provider now has 3 replicas, right? So this not only keeps the cluster actually less loaded, as well as it will avoid the problem of being idle, right? And also the users could connect to the closest and the most available endpoint, keeping the latency low and the utilization high. So with this first challenge, we set as a foundation for the rest ones, which JK is going to talk about and explain in the next slides.
Okay, as we mentioned earlier, that we leverage Spot instance to significantly cut the cost, but the challenge is Spot instance can be reclaimed or interrupted at any time. So how do we ensure the stability and while keeping the cost low? As you can see from the diagram, we divide each workload into 2 parts, a static part and the supplement part. The static part is a small fraction of the total replicas. It's always scheduled to on-demand instances or other stable, discounted pricing options like savings plan or reserve instance. This guarantees a reliable baseline capacity. The supplement part, on the other hand, runs mostly on the Spot instance when they are available. If Spot gets reclaimed, these pods can reschedule or scale dynamically. So they can schedule and dynamically even across different region, different cloud to maintain the availability thanks for the capability of Karpenter. So even in the unlikely case that all Spot instances are terminated at once, to be honest, we never seen that before. The static part can still handle the incoming request and keep the service up. For clarity, we call the static part XOD and the supplement part called X adaptive. Okay, the next slide is how to ensure the stable and cost-effective GPU provisioning. So you can see from the 2 configurations on the left, the static part, there is deployed entirely on the on-demand instances, ensuring stability and reliability. In the right, you can see we have adaptive node pool, and we can balance the cost and availability. It will first attempt to use Spot instance to minimize the GPU cost, and only fall back to on-demand instance when no suitable Spot instance available, even across different region, different cloud providers. In short, a small portion will guarantees stability, and the adapt part will ensure the cost efficiency. So the next part, okay, it's time to deploy it and how we handle the initial rollout. In practice, we start with a 2 part. For static part, XOD, we use a website like Spot Insight to check which region or cloud vendors currently have the most available GPU capacity. It's a free tool, you can check it. And then we use Karpenter to schedule these workloads into those stable regions and sufficient on-demand resources. For the adaptive part, X adaptive, we simply distribute workload evenly across the clusters at the very beginning and adjust it dynamically later based on the real provisioning and spot availability, like reschedule the pending replicas. So the next challenge is how we handle the spot terminations. In Karpenter's world, when a spot instance get reclaimed, they first attempt to find another available spot in different zones. If no spot capacity is available, it fallbacks to an on-demand instance. But if there's no capacity, this pod will remain pending. Now, this is our controller comes in. If a pod says pending for more than 5 minutes, we will reschedule it through Karpenter to other regions or cloud vendors that don't have long pending pods. In short, we keep retrying intelligently, and every workload finds a place to run. Generally, it will not cost a long time. So the next is dynamic distribution adjustment. Before we said that we will adjust adaptive parts replica distribution based on the provision status. Now let's dive into it. First, we will record the average spot node lifetime in the past 24 hours per cluster. Here's one example. If cluster A, the spot lifetime is 1 hour, cluster B is 2 hours, so the weight is 1 and 2. Then every 6 hours, we will reschedule the adaptive part replicas based on the weights. And here's some small rules. If a cluster is a newly created one, which means it has no replicas, we should schedule small part like 10% or at least one replica to prop the capacity. If no spot instance weight, we will set to 0. And after 6 hours, we'll be follow the previous rules to prop the capacity. The last rule is if no spot instance in all clusters, like Black Friday is on-demand instance, we will echo the weight and just reschedule the long pending pod into the clusters that which don't have. Okay, the next is demo time. So a little bit small, but I can explain it. But you can see there's a cluster. We have two YAML, which is for EKS, which is for the GCP. Yep, it's really small. So you can got these two cluster running, and this is the YAML. So you can just say the YAML. It's on-demand and a spot. It's for, yeah. So just apply it. Yes, let's get the pods. Yes, we got these two kind of clusters pod running. Yeah, let's see the node claims. Yeah, it's a GCP cluster. So let's sleep for 5 minutes to mimic the situation of the GPU unavailable. Yeah, there we get pause. Yeah, you can say it. You can see we got this too. We can yeah. Get the aims, yeah. Next, yeah, it's a little bit small, but you can see it works. But the its problem is this is not a out of box, and the setup is quite complex. You need to leverage Karpenter and Karpenter. So it also lacks intelligence in replica distribution. So when I say replica distribution, I mean if you have a deployment who have multiple replica, you want to put some of them on demand instances, like one of them or two of them, the rest of them on the spot instance for lowering the cost. Also, it has limited cloud provider support. Karpenter now only support AWS, but our team is expanding the boundary to the Google Cloud and other cloud. It's not a built-in pricing comparison, and we propose to improve it in several ways. Like we have a unified control plan, Kubernetes based with a Hypernode abstraction. And the Hypernode manages VMs and containers across multiple cloud providers directly. Then we can have a built-in scheduling strategies, enable the better placement and optimization. Finally, we can have a single YAML deployment run anywhere, cost effective or scalable. So I will hand over.
Yeah. So, going back to this, talking about the future real quick here, because I think JK is talking about something interesting. Did anybody here go see Corey Quinn's talk yesterday about the myth of cross-app porting? Okay, so I think Corey astutely identified a lot of the complexity and the frustration and the headache around this kind of stuff. And if you've taken anything away from the architectures we're showing here, these are complicated things to do, right? They require good ops teams. They require understanding of several different projects and how they fit across the different platforms. And one of the things that JK is referencing here about the future is we're doing this now. We're starting to explore this. We're having customers who are asking to do this kind of movement, have these kind of applications. And so in the future, we'd like to make this easier. We're trying to figure out where the bumps are, where the burrs are, and how we smooth that down so that in the future, perhaps the myth of cross-platform portability becomes just that. It becomes more of a myth, or starts to become reality, right? We start to see how we move the workloads from place to place. So I think it's a difficult challenge now, and the companies that we all represent, we're looking into this challenge and we're trying to make it better for the future. But this seems to be where the future is going in many respects. And we have many customers who are asking for this type of activity and these type of topologies. So as much as it might seem like a myth, we have to tear down that myth now. We have to end that myth, and we have to bring it to the reality that's going to be what's going to happen in the future. So with that, thank you all for coming. We've got some further research links here, so you can follow up on Karmata, you can follow up on Cluster API, you can follow up on Karpenter. As JK noted, at the moment, Karpenter is, there's two parts to Karpenter. There's the core of the Karpenter project, which is the algorithms and the scheduling and everything. And then there are provider implementations of Karpenter. And so AWS was the first implementation. There's an Azure implementation. There's a GCP implementation, Alibaba, Oracle Cloud. And there's a Cluster API implementation as well, which is still in the early days. But the hope is that through the Cluster API provider, you'll get access to 24 other providers that you can run Karpenter on top of. So I think this is really exciting. I know JK and Praseeda think it's really exciting. Thank you all for coming out.
Thank you.
Yeah,
Questions?
I think we have about a minute and a half for questions if anyone's got one. Maybe a quick question. Oh, someone just walked up to the mic there.
Yeah. So I'm an architect. I'm just wondering, right? I do work with multiple cloud providers, and this is a very great concept. I know you said still in the early phases. So is it still production ready yet or not yet? Anything that you can do production level? That's one thing that I would like to ask. The second part is the networking part. How are we gonna do the networking part, like the ingress, egress, firewall networking? Going across the clouds is not an easy thing. Security is a very complex topic, and how much pain we have to go through IT to get all of this sorted out. Right. And on top of it, any part of the authentication providers, right, that you're gonna do with your Kubernetes cluster, right? Some would support Entra, some would do, all can talk OIDC, but some would only do Entra, some will do Oktas. There's whole lot of things. So you said it's a very complex maze that you're talking about here. Yeah. But how are we gonna mitigate or overcome all of these challenges? I know it's still in beta, but right. That's what I was all thinking about all of that when you presented it.
Yeah, You're right. It is complicated. I work with customers who are doing this kind of in single cloud environments right now, and they're asking to go into multi-cloud environments, right? And so we're pushing into these realms. I think, I don't know, JK, do you have any insight on the networking though? Have you been seeing applications that want to go from one cloud to the other and talk across the networks that way?
It's really complex and hard to tackle.
Right. But this is where like virtualized networking is going to get more complicated in the future. It's going to get more integrated with these things. Yes, there are difficulties in building cross-cloud networking channels, but it can be done. And as we do it more, as customers and users ask us to do these things more, we're going to figure out where the bumps are, and we're going to smooth them down and make it better.
Yeah, man. The main problem is if you are doing barebone network like Azure or AWS, things might be much easier. But if you are going through a public route, things are. IT is not going to let you do anything.
Well, right. But those public clouds will invent features for this when it becomes demand. So we can take one more question. I know the gentleman behind you had kind of queued one up. So one more, and then we'll have to shut it down here.
Yeah, just kind of adding on to that, right? Like, does a tool are you guys thinking about on-prem GPUs to public cloud?
That's the great thing about the projects that we're talking about here. Something like Cluster API can absolutely be used on-prem. And if you have an on-prem environment that looks like a custom platform that you've built, right, with your own APIs and everything, you can build your own Cluster API provider. And in fact, I've talked with people from CERN who have done exactly this for their infrastructure. They built their own Cluster API provider to service the needs of the CERN infrastructure in Geneva at the Large Hadron Collider. So there are organizations doing this, and I would say that's the highest difficulty you can reach because you're writing your own provider. But that's the great thing about free and open source software, right? We can explore this, we can learn it, we can make the future better.
All right,
Thank you very much.
Thank you.